So good morning, and again, welcome to Physics 130. And I'm going to today start chapter 1, which is kind of a review. The physics basically starts in chapter 2. That's where we do kinematics, which is the mathematical description of motion. But before we do that, we have to define certain terms to make sure that we know what we're talking about, and also kind of review a few math things, all right? Like calculus, some algebra, some facts from geometry about spheres and cylinders and so on. So first of all, in order to talk about something moving and how much time has passed, we need to have a clear definition for the time. And the units for time, you got the day, you got the hour. So what are the SI units, the standard international or system international units are? What are they? And it turns out the time we measure it in seconds. Usually abbreviated by S, but the S sometimes looks like a 5, so sometimes I might just write SEC for seconds. The book just writes S because it's, handwriting and typed form is a little different. So sometimes I might write just S, sometimes SEC. Most likely I'll be using this. So how do we define the second? Well, a day has 24 hours, and an hour has 60 minutes, and a minute has 60 seconds. So you might say a second is the time it takes, or is 1/24 over 3600, because an hour has 3600 seconds. So if you take a day, divide it by 24, and then divide it further by 60, and divide it further by 60, you get the 1 second. So that's how long you have to wait for a second to pass. A different way to define it is, if you get a pendulum like this, we will talk about pendulums when we talk about oscillations, and if it's oscillating, you might define a second as, for a certain length, it's the amount of time it takes to make one oscillation. Let's say if it starts here, it goes this way and comes back to the original place. That's 1 second. But these are not very, they're good, they're okay, the good starting points, but they're not accurate. So I will just read the definition of a second. You can read it, it's in the book. So it says 1 second is the time required for 9,192,631,770 oscillations of the radio wave absorbed by the cesium-133 atom. And that's it, that's the definition of a second. So why do I mention it? Well, so that when we say a second, rest assured that we know what we're talking about. So that's out of the way. Okay, the next thing is we have to be able to talk about, so that's time, but in order to tell how fast something is moving, so it's covering a certain distance over a certain time. So what is the standard unit for distance? That's the meter. So time, and then length. The standard unit for length is the meter. All right, is the meter. The abbreviation for a meter is M. So what's a meter? Well, arbitrarily somebody can say the length from here to here is a meter. All right? If you want a meter like it, well, I will save this meter stick, and if you want one like it, come and duplicate one. So you come in, you put a piece of wood next to mine, or a piece of iron, whatever, and just cut it to be exactly this same length. And if you want 2 meters, well, make it twice as long. If you want half a meter, cut the thing in half and make sure the two pieces are equal length, and that's half a meter. If you want a quarter, I'll cut it in 4 pieces. If you want 1/5, cut it in 5 pieces and make sure the 5 pieces are equal, and that's 1/5. If you want what's called a centimeter, it's 100ths of that, cut it in 100, and that's 1 centimeter. And for a while, that was good, and it works pretty well. But now it's defined in terms of the speed of light, because the speed of light turns out to be a really good measurement because it's constant. It has a set value. And so I will also read it. It says 1 meter is the distance traveled by light in vacuum during 1/2 299,792,458 of a second. So take a second divided by this large number, 299,792,458, and that's the distance that light travels in that duration of time. So we needed the second, right? You needed the second that we defined earlier in terms of the oscillations or the of the radio wave absorbed by the cesium atom. We needed the second to define now the meter. Okay, so now you got the meter and you got the second. So when we say a 1 second, we know what we're talking about, and when we say 1 meter, rest assured that we also know what we're talking about. The next thing is mass. And for a while, that's all we need, these. Because we can combine them. Length and time will give us speeds and accelerations. Mass and some combinations of length and time will give us momentum and force and so on. Okay? So the mass, the standard unit is the kilogram. And it's abbreviated as kg. And by the way, let me just back up a little bit here. There is a meter, and of course there is the centimeter. 1 meter has 1,000, has 100 centimeters, and it has 1,000 millimeters, millimeters. And there is the kilometer that has 1,000 meters. So feel free to review those there in the book. I don't think they're worth spending the time, especially that this is your second physics course. So now the kilogram, 1 kilogram is also, you get it has 1,000 grams, usually 1,000 grams. And you have the ton, which usually you almost never see. Anyways, so you have these units here. The time, you get seconds and hours and minutes. Okay. So a kilogram. So how do we define a kilogram? Well, for a while, actually for a long while, there is a cylinder in Paris, and it's, I'm reading here. So it was a cylinder similar to this. So it says here, the definition of a kilogram is is the mass of the international standard kilogram, a polished platinum iridium cylinder stored in Paris. And so there is a cylinder in Paris somewhere, and it's circular. It's an alloy. It's a mixture of platinum and iridium, and that is the definition of a kilogram. So they say, all right, here's my cylinder. If you want a kilogram like it, you can put it in a balance, and we can talk about those also how when we do Newton's laws, because the balance will assume the existence of gravity. Anyways, let's say we're on Earth. If you want a kilogram like it, put it on a balance. If they balance, then you have exactly a kilogram like it. If you want 2 kilograms, make 2 duplicates. If you want 3 kilograms, 10 kilograms, just keep duplicating. If you want half a kilogram, slice it in half. Make sure the 2 pieces have equal mass, and you have half a kilogram. So you can make fractions of it, you can make multiples of it, and you have a kilogram. Great. So that was it. So let me put these 2 away. Here. Now, if you have a like a cylinder like that, it's not a really good standard. I say not perfect. Not if you leave it for 1,000 years or 5,000 years, it might get lost. It might get stolen. So it's made of platinum, mostly platinum, like 90%. So in 2019, May 20th, 2019, very recent, basically last year, the definition of the kilogram has changed, basically shortly after our book was published or printed. The kilogram is now defined in terms of the speed of light, the cesium transition frequency, the one we use to define the time, to define the time, and then in terms also of Planck's constant. Okay, Planck's constant, you will learn about it in the 3rd semester of this course. Okay, so the kilogram has been redefined now as basically last year. Okay, so Anyways, why did I mention these or even spend time? So that the reason we spend time is so that we know exactly what we're talking about when we say 1 second, the length of a meter, and the kilogram. So we just want, in science, we want to have clear definitions and clear standards so that if we do an experiment, it gets duplicated and it gets replicated with no problems. Okay? So now I want to do two examples. Let me make sure it's recording here. Okay. So the first example I would like to do is I want you to do the following. Here's the exercise. Let me just write it down. Exercise or example. To show you how to estimate and review scientific notation and powers of tan and so on, and unit conversion. So make reasonable assumptions. So make reasonable put the codes here, assumptions. To estimate the following. 1, the radius of Earth. Okay. 2, so the first, I want you to estimate the radius of the Earth. The second one, I want to find the mass of Earth. And number 3, the mass of all water on Earth. Right. So I want us to estimate the radius, not radian, radius of Earth, mass of Earth, and the mass of all the water on Earth. And how do we begin? All right. So with this, I said make reasonable assumptions. So maybe it's not. We have to refer to things that maybe that are in quotes also common knowledge. So it's common knowledge that the time difference between the East Coast and the West Coast is 3 hours. Okay, 3 hours between the East Coast and the West Coast. So here's what it is. So here's Earth. As you know, it's round, not a perfect sphere, but good enough to estimate it, to approximate it as a sphere. And so here is, let's say, here's the East Coast, and here's the West Coast, and the Earth is spinning. Let's say it's midday on the East Coast, so the sun is shining here, basically right above it. We know that the time difference between East Coast and West Coast is 3 hours. What does it mean? If it's midday here, it's 9 a.m. for us. So how long do we have to wait for the sun to be directly above us? We have to wait for 3 hours. So the Earth will spin. After 3 hours, the sun will be right above here. Okay, so it will turn this way. So the Earth is turning, spinning about its own axis. So in 3 hours, the Earth will turn by this far. In 3 hours, it will turn by this far. Okay. Well, how far? What is this far? How long is it? How far is the East Coast from the West Coast? Turns out that it's 3,000 miles. A little bit less, 2,800, 2,900, but let's say about 3,000 miles. So the Earth has turned by 3,000 miles in 3 hours. So it's spinning by 1,000 miles every hour. So in 24 hours, it will make one turn. So in 24 hours, the distance it will spin by is 24,000 miles because it's making 1,000 miles per hour. So we conclude that the circumference, okay, it's a circle, it's a sphere, so this side here is circular, and the circumference, which is equal to 2 pi times the radius, 2 pi times the radius, here is the radius, 2 pi r, that is 24,000 miles. 24,000 miles. So let's find the radius. So the radius, therefore, would be the circumference divided by 2 pi. So now we're going to estimate. We're not going to use a calculator. 2 pi is about 6. Pi is an irrational number. It's 3.14159. It goes on. So 2 pi is about 6. And 24,000 divided by 6 is approximately 4,000 miles. 4,000 miles. I looked up this number. It turns out that the actual value, the average radius of Earth, on average, it's 3,958. 3,958.8 miles. On average, that's what it is. So we're very close, all right? And we have estimated the radius. It's about 4,000 miles. Let me change that to kilometers. 1 mile has about 1.6 kilometers. So I have 4,000 miles, and then I need to change to kilometers times 1 mile, there are 1.6 kilometers for every 1 mile, so the miles would cancel. And I do 4,000 times 1.6, turns out to be 6,400 kilometers. And let's write it this way. R would be 6.4 times 10 to the 3. Because 10 to the 3 kilometers, right? Because 10 to the 3 is 1,000, so 6.4 times 1,000 is 6,400. And let me change it to meters. 1 kilometer has 1,000 meters, so you multiply this by 1,000, it becomes 6.4 million. So 6.4 times 10 to the 6th. So let me write it this, right? So R is 6.4 times 10 to the 6 meters. That's the radius, all right? So that's the one I'm going to be using. Because the standard units for length will be meters. So I want to use meters. Okay. So the next thing, it says estimate the mass of the Earth. How much mass is on the Earth? How do we estimate it? Well, if Earth were made of water, you might guess, actually I'll give you a moment to think about it. What do you think we will need? What information do we need? We have the radius. What information do we need to find the mass of the Earth? Think about it. I hope you have thought about it for a moment. And the information you need is the density of Earth. How many kilograms can we pack? So we need to first find the volume of the Earth, and then remember density. If you remember from chemistry or physics, when you took the first one, density is the mass over the volume. So density has the symbol, let me use yellow chalk. Density has the symbol rho, mass has the symbol m, and capital V is the volume. So the mass will be the density times the volume. So if I know the volume and I know the density, I will know the mass. I could calculate the volume. Let's find the volume first. All right, so now, that's why I'm doing this exercise, because we're reviewing geometry also, and powers of 10, and estimating. So what's the volume? Well, if you assume the Earth is a perfect sphere, a sphere has a volume of 4/3 pi r cubed. So that's 4/3 times pi r cubed. Well, r is 6.4 times 10 to the 6th. So I have 6.4 times 10 to the 6th. And I have to cube it. Notice I don't put the units till the very end. And often I don't even put the units because it's clear from the context, I believe. So at this point, you can go ahead and use your calculator and find it. But I'm not. I will not use my calculator because the point of this exercise is to show you how to estimate and how to avoid using a calculator. So first of all, 4/3 times pi. Pi divided by 3 is approximately 1. me put approximation. So this thing here is approximately 1, so basically they cancel. It's 1.0 something. And then 4. So I have 4. And then I have here 6.4 to the power 3. 6.4 to the power 3. And then 10 to the 6th power, and that has to be cubed also. Okay? So first, let me do this. 10 to the 6th to the 3rd power, you multiply the powers. So 6 times 3 is 18, so this becomes 10 to the 18th power. And here I have 4. I'll put approximation marks again. Now 6.4 cubed, what is it? First of all, if you do 6 cubed, it's 216. And if you do 7 cubed, it's 343. Somewhere between 343 and 216. And it's biased toward the 200. So I will use, a good number would be 250. Instead of 216, instead of 343, it's somewhere in between. It's 250. 250. And I believe the answer is around 260, 270. I did not do it by calculator. I should have done it, but I didn't. Anyways, 250 is good enough. And then 4 times 250, that's why I like 250, is 1,000. 4 times 250 is 1,000. And then 1,000 times 10 to the 18th power, 1,000 is 10 to the 3, and 10 to the 3 times 10 to the 18 is 10 to the 21. It's 10 to the 21. So that's the volume here. That's the 10 to the 21 what? Well, no units, no units. R cubed is in, R is in meters, so meters cubed. So it's cubic meters. So that's the volume of Earth, approximately. And if you go to, actually I didn't look it up. I was saying, if you go to Google and find the volume of Earth, it would be really fairly close to this. Maybe 5 times 10 to the 21, maybe 2 times 10 to the 21, maybe 7 times 10 to the 21, somewhere in that ballpark, somewhere in the 10 to the 21, maybe 9 times 10 to the 20, maybe 10 to the 22, somewhere really close to this, okay, within a factor of 10. So now the mass, I found the volume. The mass would be the density times the volume. So what would the density be? So I have the mass is the density times the volume. What's the density? Well, we have to make certain assumptions. Earth, is it made of steel? No. Is it made of water? No. Is it made of sand? Sand? No. So it's denser than water, denser than sand, but not probably as dense as iron. So water has a density of 1 gram per cubic centimeter, or 1,000 kilograms per cubic meter. Water is 1,000 kilograms per cubic meter. So let me write it here. The density of water, it happens to be 1,000 kilograms per cubic meter. Density of sand, if you may guess, it's approximately 3,000 kilograms per cubic meter. Density of iron is approximately 7,800 kilograms per cubic meter. About 8,000 kilograms per cubic meter. Somewhere between iron and sand. Maybe biased toward the iron. So let's add them and just average. So this is about 8,000, this is 3,000. 8,000 plus 3,000 is 11,000, and you divide by 2. So just average it. So 5,500. So the density of Earth is approximately, maybe 5,500. I don't know. It could be 5,000. It could be 6,000. 5,500 is okay. So 5,500. So 5,500. That's an assumption. And then times the volume of Earth, which we estimated to be 10 to the 21. So the mass will be, this is 5.5 times 10 to the 3, and then times 10 to the 21. So the mass of Earth is 5.5 times 10 to the 24 kilograms. That's the mass of the Earth. We estimated. Now you can go ahead and use Google. And according to Google, or the book also, you can find it, the actual mass, or the more approximate, is 5.97 times 10 to the 24 kilograms. Okay. Very close. So, again, the point of this exercise is to show you how to make reasonable assumptions to estimate things. It's a very good skill that you would get out of this physics class, and if you continue with the sequence, it's a good habit to have as a physics person, as a science, as a math person, as an engineering person. It's a good skill to have. You can look at anything and make reasonable assumptions to estimate that thing. Okay, great. So now we're almost done with this, but we have one more question. The mass of all the water on Earth. We need to estimate the mass of all water on Earth. How are we going to do that? Well, in order to do that, we know that this Earth's surface area is 3/4 water. So let's find the surface area of Earth. So let me put here the surface area of Earth. It's a sphere. What's the area of a sphere? If you remember, the area of a circle is pi r squared. It's an area, so it has to be length times length, so r squared. But for a sphere, it's not just a circle, it's the whole surface area. It turns out to be 4 pi r squared. So let's do that. So you get 4 pi times the radius squared. But the radius of Earth is here, 6.4 times 10 to the 6th. So 6.4 times 10 to the 6th. But we have to square it. So the area will be 4 pi, that's about 12, right, approximately 12. And then 6.4 squared. What's 6.4 squared? 6 times 6 is 36, and 7 times 7 is 49. So I'm guessing about 40. And then 10 to the 6 to the 2 is 10 to the 12th. 10 to the 12th. And let's multiply these. 12 times 40 is 480. That's about 500. So it's about 500. I put here approximation marks. 500 times 10 to the 12, and that's about 5 times 10 to the 14 square meters. That's that. So if you go on, again, Google, and find the surface area of Earth, total area of Earth, including the water on it and everything, it's 196.7 million square miles. That's about 500 times 10 to the 6 square kilometers, which is about 5.04 times 10 to the 5.04 times 10 to the 14 square meters. So the actual value turns out to be about 5.04 times 10 to the 14 square meters. We're extremely close, right? Very close. 5 times 10 to the 14, they're saying 5.04. We're lucky. Very close. Okay, very good. So now, the water covers 3/4 of that. So about 4 times 10 to the 14, 5 times 10 to the 14. And so what's the mass of the water? So let me use my marker here. I will copy this number here. The area is 5 times 10 to the 14. The area is 5 times 10 to the 14 square meters. So the area covered by the water, I'll put it here, AW, is 3/4 of this. What's 3/4 of that? Well, 3 times 5 is 15 over 4. That's about 4. About 4 times 10 to the 14 square meters. 4 times 10 to the 14 square meters. So that's the area, but then I need the depth, right? It's like, imagine you have a really big pool. It has a certain area. To find the volume, you multiply the area by the depth. What's the depth? Well, the oceans, sometimes it's shallow, sometimes it's deep. It says deep, I think, is 10 kilometers or so. So let's just take, on average, it's 1 kilometer. Maybe it's 2 kilometers, I don't know. So let's just say 1 kilometer for the depth. So the volume of the water would be the area of the water times the depth of the water. And the area of the water is about 4 times 10 to the 14. And then the depth of the water is about 1 kilometer. That's 10 to the 3 meters, right? 10 to the 3 meters. So the volume of the water will be 4 times 10 to the 17 cubic meters. And water has a density of 10 to the 3, as 1,000 kilograms per cubic meter. So the mass of the water will be the density of the water times the volume of the water. The density of the water is 1,000, or 10 to the 3, and the volume is 4 times 10 to the 17. And so we get about 4 times 10 to the 20 kilograms of water on Earth. I looked it up. It turns out to be 1.4 times 10 to the 21. So about 3 times this amount. 1.4 times 10 to the 21. So they estimated that the mass of the water is about 3 times this amount, which is fine. We're here talking about orders of magnitude. As long as, if you're off by a factor 3, 4, 5, even 10, that's fine, because you're just estimating. We're not looking for accuracy, we're looking for estimate. Okay, I will pause here and we will go to the next problem.